everyone. So today we're continuing chapter 19, electrochemistry. Last time we saw some examples of different calculations that we might perform with electrochemical cells. And we got a little bit of practice with assigning anodes and cathodes and figuring out the spontaneity of electrochemical cells. So today we're going to start by predicting whether a metal will dissolve in acid. So remember, we kind of base all of our half reactions and their potentials off of a standard hydrogen electrode. So remember that big long table we saw, table 19.1. And right in the middle, or kind of in the middle, was that standard hydrogen electrode where hydrogen ions were reduced to hydrogen gas. So they gain electrons. Now, metals whose reduction half reactions are listed below the reduction of hydrogen to ions to hydrogen dissolve in acids. So as an example, off to the right, we have zinc dissolving in acid, and the zinc initially is pure and it has an oxidation number of 0. And then when it reacts with hydrogen ions in solution, which have a +1 oxidation number, zinc will become ions with a 2+ charge. So those the oxidation number there would be +2. And then hydrogen gas is one of the other products, and that will be pure, so it has an oxidation number of 0. So zinc is losing electrons, so it is oxidized. And then hydrogen, as we said before, is being reduced. Now, remember in that big long table, and in fact, let me skip ahead to that table, we saw that anything above the standard hydrogen electrode liked to be reduced. So those were stronger oxidizing agents, so more likely to be reduced. So if we tried to, let's say, dissolve copper. So let's say we try to dissolve copper in hydrochloric acid. We just saw with the example of zinc, oops, I don't know what I did there. We just saw with the example of zinc that when it reacts with hydrogen ions from an acid, it's oxidized. But according to this table, copper likes to be reduced. So copper is not going to react in the same way with hydrogen. In fact, it's not going to react and it won't dissolve in hydrochloric acid. However, anything listed below the standard hydrogen electrode will dissolve in acid, or any of the metals at least. So again, that's because the ions listed below the standard hydrogen electrode are stronger reducing agents, so they're more likely to be oxidized. And that's exactly what we want if we're trying to dissolve a metal in acid. We want the metal to oxidize. So again, if something would rather be reduced, then it's not going to dissolve in acid. Okay, so let's go back. So again, metals listed above the standard hydrogen electrode in table 19.1 do not dissolve in acids. Now, almost all metals will dissolve in nitric acid. So let's go back to our table. So let's find nitric acid. Let's see, so that's here. So nitric acid is listed above the some of these metals here. So nitric acid can dissolve some metals such as silver, iron, copper, tin, etc., whereas hydrochloric acid cannot. So that is one exception there. All right, and so what ends up happening there, so let's say we have nitric acid. Again, its half reaction involves 4 hydrogen ions and 3 electrons. So this was balanced assuming an acidic environment, which makes sense. It's nitric acid. And in this half reaction, instead of reducing hydrogen like we did with hydrochloric acid or our acid example with zinc, the nitrogen will be reduced. So that makes this a little bit different. And that means that anything listed below nitric acid on that table can be reduced by nitric acid. Now, there are some metals that typically don't corrode when they come into contact with acids, such as silver, gold, and platinum. However, silver and platinum can dissolve in nitric acid and hydrochloric acid mixed together. So there are ways to corrode those particular metals. All right, so worksheet problem 5. Let's determine whether or not each metal dissolves in 1 molar hydrochloric acid. For those metals that do dissolve, write a balanced redox reaction showing what happens when the metal dissolves. All right, so copper we kind of already mentioned, right? If we go back to our table, copper is listed above the standard hydrogen electrode, so it does not dissolve in hydrochloric acid. And I'm just going to write a note here that the reason it does not dissolve is because copper would rather be reduced than oxidized. All right, what about iron? Let's go to our table. So iron is not one of the metal. Oh, well, it is listed. Well, so this one here, that's iron 3 plus turning into iron 2 plus. So that's not a pure metal. So let's keep going. So I don't see it. Here we go. So it's listed here and here. So iron is listed below the standard hydrogen electrode, which means it prefers to be oxidized. So that's perfect because then hydrogen can be reduced and we'll end up with iron ions and hydrogen gas. Okay. All right, what about silver, Au? Let's go down the list. It's right here, kind of towards the top. So Au also does not dissolve in hydrochloric acid because it is listed far above that standard hydrogen electrode. So silver would also prefer to be reduced rather than oxidized. All right, so now that we figured out that iron can dissolve in hydrochloric acid, let's write a balanced redox reaction showing what happens when the metal dissolves. All right, so for this one, I think I'm going to use Fe solid, and I'm going to use the 2 plus ion for this because it'll just be easier to balance. All right, and then so iron is going to be oxidized. It's going to lose electrons. And then we said that hydrogen ions will be reduced. So they're going to gain electrons and become hydrogen gas. Okay, so we have 2 electrons for both equations. That's kind of why I chose the 2+ version of iron here. And we're going to cancel our electrons and write out our balanced reaction. Okay, so very similar to the reaction with zinc, but this time we have iron. Okay, so let's go past our table. All right, so the next thing we're going to discuss are the relationships between the cell potential, E cell, Gibbs free energy, delta G, and the equilibrium constant, K. So you'll notice in the figure down below, there's this little triangle showing how all of those different variables connect to each other or relate to each other. And we're going to step through all of these different equations. So we have already seen this equation where the Gibbs free energy is equal to negative RT times the natural log of K. So we have seen that before. Let's see, so now we're going to learn a couple of new equations that we can use. So there is a relationship between the Gibbs free energy and the cell potential. So delta G under standard conditions is equal to negative N times F times the cell potential. So in this equation, N is the number of electrons in a redox reaction, so the number of electrons that are transferred. And this is why it's really important to know how to balance half reactions, because you need to have the same number of electrons that are transferred from one half reaction to another. And then we can use that number of electrons in our calculation. And then F is Faraday's constant. So this constant is equal to 96,485 coulombs per mole of electrons. So we talked about coulombs previously. So if you don't remember what coulombs are, make sure to go back and review your notes. Okay, so basically for this equation, let's say we're trying to solve for Gibbs free energy. We would first probably need to figure out what the cell potential is, and we can figure that out using this equation that we've used previously, where we take the potential of the cathode and subtract the potential of the anode. And then we just plug that in, as well as the number of electrons that are transferred and Faraday's constant. All right, so let's focus on this equation for a little bit, and then we'll move on to the other equation down below. So we're going to use tabulated electrode potentials, so those are the E values, to calculate delta G for the reaction, where iodine reacts with 2 bromide ions to produce 2 iodide ions and bromine. And we're going to determine if this reaction is spontaneous. All right, so we just said that E cell is equal to the cathode potential minus the anode potential. So we'll have to figure out what's being oxidized at the anode, what's being reduced at the cathode. And then once we have our E cell value, we're going to plug that into this equation that we just learned. Okay, so let's start by figuring out what's reduced and what is oxidized. So I'm going to rewrite the equation down below just so it's a little more visible. And I'm also going to leave out the states because they take up a lot of room. Okay, so let's assign oxidation numbers. So I2 has an oxidation number of 0 because it's just its elemental form. Bromide has a -1 charge, so its oxidation number is -1. Same for iodide. And then bromine, Br2, is the elemental form of bromine, so that has an oxidation number of 0 as well. All right, so if we just look at iodine, the oxidation number changes from 0 to -1, so is that a loss or gain of electrons? It's a gain of electrons, so is it oxidized or reduced? Reduced. And then bromine, its oxidation number starts out at -1 and goes to 0, so is it losing or gaining electrons? Losing electrons. It's becoming more positive. So then is that oxidation or reduction? Oxidation. All right. Great. So let's write out our two half reactions. So our oxidation half reaction involved bromide becoming bromine and losing 2 electrons. And then the reduction half reaction involved iodine gaining 2 electrons to become 2 iodide ions. Okay, so does oxidation occur at the cathode or the anode? The anode. And does reduction occur at the cathode or the anode? The cathode. It's the only one left. Okay, so let's look up these E values for the bromine half reaction and the iodine half reaction. So if you want to pause the video and do that, you can. So the potential value for the bromine half reaction is 1.09 volts. And the potential for the iodine half reaction is 0.54 volts. Okay, so let's plug that into our equation for E cell. So we're going to take the cathode value and subtract the anode value. So the cathode value is 0.54 volts. And then we're subtracting the anode value, which is 1.09 volts. Okay. So we're ending up with a negative value, 0.55 volts. So we can probably already tell whether this is spontaneous or not, right? Without even calculating delta G. So do you remember, if E cell is negative, does that mean it's spontaneous or non-spontaneous? So it is non-spontaneous. So we can already tell this is non-spontaneous. So knowing that, will delta G be positive or negative? It should be positive because remember delta G is positive for spontaneous or non-spontaneous reactions and negative for spontaneous reactions. So it does get a little frustrating sometimes because we have to remember the signs for all of these different variables and what they mean. So making flashcards can help, or just making a little chart could help too. All right, so let's calculate delta G. So we predicted that it will be positive. So remember, it's equal to negative NFE cell. And remember, N is the number of electrons that are being transferred. So looking at our half reactions above, 2 electrons are transferred, and their amounts are equal, so we didn't have to do any balancing here, which is good. But sometimes you will have to balance in order to get the same number of electrons. Okay, so what we'll do is write in negative, oops, my thing isn't working, there we go, negative 2 moles of electrons times Faraday's constant, which was 96,485 coulombs per mole of electrons. And then we'll multiply that by E cell, which was negative 0.55 volts. All right, so we have two negatives, so we can already see this will be positive, which matches what we predicted. And when we plug those numbers into our calculator, we get 1.1 times 10 to the 5th coulombs times volts. That's a weird unit. So in a previous lecture, we talked about how a volt, and I'll write this down below, 1 volt is equal to 1 joule per coulomb. Okay, so if we rearrange that, 1 joule is equal to 1 coulomb times a volt. So we can rewrite the unit for this answer as joules. So if you have coulombs times volts, that is equal to joules. Okay, so we already concluded that this was a non-spontaneous reaction. So the reverse reaction would actually be spontaneous. All right, and that does kind of make sense with our potential values. So bromine has a pretty high positive value. So that means it would prefer to be reduced, not oxidized. And iodine has a lower positive value, so relative to bromine, it would prefer to be oxidized. Okay, so let's work on worksheet problem 7. What we're going to do here is work on number A, or letter A together, and then I'll let you work on B and C on your own. And then you can look up the answer and see if you got the same thing on the worksheet key. So for part A, we're going to use tabulated electrode potentials to calculate delta G for each reaction at 25 degrees Celsius. So we're under standard conditions here. Okay, so let me just get my notes out. All right, so for A, remember the first thing we always want to do is assign oxidation numbers. So for iron 3 plus, that would just be the same as the charge, plus 3. Tin is just in its elemental form, so that would be 0. And then in the products, iron is in its elemental form, so that would be 0. And then tin 2 plus would be plus 2. All right, so let's look at iron. Iron goes from plus 3 to 0. So is that oxidation or reduction? So that would be reduction. It's gaining electrons. And then tin, is that oxidation or reduction? Oxidation, it's losing electrons. Okay, so we have our two half reactions. So let's write them out. So we've got 2Fe3 plus, and that is going to gain some electrons. We'll figure that out in a second. And then it will become 2Fe. So this is our reduction half reaction. And then our oxidation half reaction, we've got 3 moles of tin becoming 3 ions, and then they're going to gain some amount of electron, or lose some amount of electrons. Okay, so if we have 2 3+ ions for iron, how many electrons does each ion have to gain to become neutral? So each of those ions would have to gain 3 electrons, right, to become neutral. And we have 2 of those ions, so that would be a total of 6 electrons. Now what about tin? How many electrons does tin lose? So we've got 3 tin 2 plus. So each tin is losing 2 electrons, and we have 3 of them. So it's losing 6 electrons. Okay, so that's good. That means that our electrons match for the reduction and oxidation half reaction, so we don't have to adjust anything there. So now let's look up the potential values for both of these half reactions. So for iron 3 plus, its value is negative 0.036 volts. And then for tin, it's negative 0.14 volts. And remember, it's really easy to mix up the iron 2 plus half reaction and the iron 3 plus half reaction. So always make sure to look those up and make sure you're choosing the right one. Okay, so let's calculate E cell. And remember, it's cathode minus anode. So let's see, is the reduction half reaction at the cathode or the anode? It's at the cathode. And is oxidation at the cathode or the anode? The anode. Okay. All right, so we'll take the cathode value, negative 0.036, and subtract the anode value, which is negative. So negative 0.036 plus 0.14 will give us 0.104 volts. All right, so E cell is positive. So is this spontaneous or non-spontaneous? It's spontaneous, so this is perfect. It makes sense. Okay, so now let's calculate delta G. So negative NFE cell. So the number of electrons is 6. And then Faraday's constant, 96,485 coulombs per mole of electrons. And then the E cell value is 0.104 volts. So if we plug that into our calculators, we should get a negative value because there's only one negative sign there. But we already said this reaction is spontaneous, so that makes sense. Delta G should be negative. Okay, so we have negative 6 times 10 to the 4th joules. Now, I skipped ahead because I could see that the units would be coulombs times volts, and we already said that that's equal to joules, so I just skipped that step. Okay, so delta G is equal to negative 6 times 10 to the 4th joules. So now you're going to do the same thing for parts B and C, and you're going to calculate first the E cell value, so the cell potential, and then Gibbs free energy using the same method. Okay, so now let's calculate the equilibrium constant for each of the reactions in problem 7. So what we'll do is go over part A together, and then you can work on parts B and C on your own. So for A, we already calculated delta G. So actually, let me go to A. Oops. I am at A, apparently. Okay, so for A, we already calculated that delta G is equal to negative 6 times 10 to the 4th joules. And then previously we've said that delta G is equal to negative RT times the natural log of K. So what we're going to do is solve for K, the equilibrium constant. So we're trying to get that value there. So what we'll do is plug in everything we know and then rearrange and solve for K. So let's plug in our delta G value. And then we're going to plug in the gas constant, which we want the one where the units are in joules. So this will be 8.314 joules per mole Kelvin. And then the temperature is 298 because the temperature in the previous problem was 25 degrees Celsius. So if we add 273, we get 298. And then we have the natural log of K. All right, so if I rearrange and just solve for ln of K, we should get a value of 24.14, and that's positive. So all I did there was I took negative 6 times 10 to the 4th and divided it by negative 8.314 times 298. All right, so now let's solve for K. So to get rid of that natural log, we're going to raise each side. So we'll have an exponent, and we'll raise that to 24.14. And when we plug that into our calculator, we should get a value of 1.71 times 10 to the 16th. So that's a really large value of K. So does that make sense with what we know about that reaction? So remember, we already determined the reaction is spontaneous in the forward direction. So that means we should produce a lot of product. And remember, the equilibrium constant, K, is equal to products over reactants, whether that's in concentration or pressure. So if we have a lot of products, then that means K will be quite large. It will be greater than 1. So that all checks out. That makes sense. So it's always good at the end of a problem just to ask yourself, does that make sense? Is that the answer I was expecting? And then if it's not, you can always go back and double check your work. All right, so we're going to stop there today. Next time, we'll talk about that last equation where E cell is equal to 0.0592 volts over N times log of K. So that will be our last equation that kind of connects all of those different variables we saw earlier. So I will see you then.